I'm Greg Johnston. I'm a senior application specialist with sensors and software, and have been with the company for 26 years. Cross-sections are the building blocks of the vast majority of all GPR data collected. Understanding the signals that you see in a GPR cross-section is critical to your success with the technology. In this webinar, I'm going back to square one and talking about how to look at a GPR line and understand what you are looking at. This is the first step to make the best possible interpretation of your GPR data. When I was putting this webinar together, I quickly realized that I have more than an hour of material to present. So you may have noticed that I added the words part 1 to the title. That is because this is going to end up being a two-part webinar. Most GPR manufacturers, including sensors and software, make GPR systems that, once you set the parameters, are pretty easy to use. Now, I would argue that sensors and software does this best with our systems, but I think you can forgive this bias. The point is that if you can cut your lawn, push a shopping cart, a baby stroller, or even if drive a car, you can probably call yourself a GPR system operator. The problem is not collecting the data, but understanding what the data is telling you about the subsurface. Most people agree that interpreting the GPR data is the hardest part of the whole exercise. So let's talk about this. GPR sends a pulse of radio frequency energy into the subsurface and records the echoes or reflections that come back. Reflections are what GPR data mostly consists of. In this conceptual animation, why does the GPR pulse reflect from the round object? Energy reflects when there's a contrast of materials, specifically a contrast in a material property called the dielectric constant or relative permittivity. You can look up the details of this property, but in my mind, the details of the property or even the name is not that important to know. It is only important to understand that a change in this property is what causes GPR energy to reflect. We understand this intuitively because every day we look in mirrors and we use flashlights and car headlights that reflect off objects. Here's another animation that shows the concept of what happens when a GPR pulse is sent into the subsurface and reflects from a boundary between two contrasting layers. It is interesting to watch this for several reasons. One reason is the complex shape of the reflection, even from a relatively simple interface. Imagine how complex it can get if the surface was rougher and the layers were full of objects that caused other reflections. The other reason this animation is interesting to watch is to see that not all the GPR energy that hits the boundary reflects back to the surface. Some of it transmits through the boundary and keeps traveling downward. In fact, if you watch it a few times, you can estimate how much of the GPR energy reflects versus transmits through. If the GPR energy just before the interface is 100%, you can see that about 30% of that energy reflects and 70% transmits through. Again, we are familiar with this phenomenon. Anytime you look out a window at night, you are experiencing energy transmitting and reflecting at the same time. In this example, light rays, but GPR signals do the exact same thing. Okay. So what controls how much energy reflects? It is controlled by the contrast of the materials. Let's look at the dielectric constant values of common materials. Dielectric constant is depicted as K for short, so you will sometimes hear me call it K. You can see here that, except for the metal at the bottom of the table, most materials have a dielectric constant between 1 and 80. The two extreme materials in this range are air at 1 and water at 80. Everything else is in between. Ice is 3, dry sand is 5, granite is 6, silty soils are 30, clays are 40. Again, what controls how much energy reflects at a boundary between the materials? The contrast in the dielectric constant between the two layers. The bigger the contrast, the more GPR energy that reflects. That is called the reflection coefficient. And here's the formula for calculating it. Let's look at some examples of this. Going from dry sand with a K of 5 to rock with a K of 6. When you do the math from the formula on the last slide, the reflection coefficient is only 5%. That is, 5% of the GPR energy that hits this interface reflects, and 95% of it transmits through. This means that this boundary will be a very weak reflector and probably very difficult to see. Here's an example that shows a weak reflecting boundary. I suspect a boundary with only 5% reflection coefficient would not even show up as well as it does in this image. Okay, let's add water to that dry sand and make it wet sand. So now we are going from a wet sand with a K of 25 to rock with a K of 6. The reflection coefficient is 34%. So we get a lot more energy reflecting and therefore a stronger boundary in our GPR line. Keep in mind that the only change in this scenario is that the dry sand is now wet sand. So let's talk about this for a minute. Water has a very high dielectric constant, 80, much higher than dry sand or almost any dry material like soil. When you replace the air, which has a very low K of 1 in the pores between the grains, with water that has a K of 80, even though the pore space is a small percentage of the total volume, it drives up the bulk K for the soil. In fact, the presence of water in a soil has the largest effect on the K value of that soil. Notice the range of values. Dry sand is 5. Wet sand is 25. If you go to a swampy mixture like a quicksand, you can even get values of K that are more than 50. Simply put, the more pore space with water in it, the higher the K value for that soil. So, when you have a dry sand with a K of 5 over a wet sand with a K of 25, 38% of the energy reflects from this boundary, a significant amount. Now, some of you may realize that this boundary is called the water table, and it can be a very strong reflector when you collect GPR data over coarse-grained sediments. Here's an example of a water table reflector. You can't help but notice how strong it is, but also notice how it cuts across dipping reflectors in the GPR line. Also notice the reflectors under the water table. There's this myth that I hear constantly that GPR data cannot penetrate water-saturated soil. People say things like the GPR survey failed because it rained last night. To those people, I present this GPR line. Let's talk about a different type of target, an air-filled cave. Going from a K of 6 for the rock to a K of 1 for the air in the cave gives you a reflection coefficient of 42%. 42% of the GPR energy that hits this boundary reflects from it. This will definitely produce a strong reflection. Here's an example of this type of reflection. Not exactly a cave, it's a road tunnel, but the results are the same. you can see the strong reflectors from the rock-air interface at the top of the tunnels. The next interface is water with a K of 80 over rock with a K of 5. This gives a reflection coefficient of 57%. This type of survey is also known as bathymetry. Here's an example of bathymetry data. Notice that it's not completely over rock. The strong chaotic reflectors here, and you can also see underneath here, are granite. But there are also reflections from the soft water-saturated sediments on the bottom of the lake, which you can see, and you would predict to have a lower reflection coefficient because what we're talking about here is water over water-saturated sediments, which means their K values are very similar, which would give you a smaller reflection coefficient. And you can see that. You can actually see this reflector get weaker along there. One of the naturally occurring boundaries that has the highest reflection coefficient is ice, with a K of 3 over water with a K of 80. This gives a reflection coefficient of 67%. Here's an example of data collected on a frozen lake. Notice how the reflection at the ice-water interface dominates the GPR line. This strong reflection coefficient is why ice profiling is one of the easiest applications for GPR. It is the reason why we built the ice map system, a GPR specifically designed for measuring ice thickness. You see this type of system on shows like Ice Road Truckers, a show about the truckers who haul heavy loads across frozen lakes and rivers in northern Canada and Alaska every winter. The last interface I want to discuss involves metal. Metal actually has an infinite dielectric constant. So when you do the math from the formula, it has a 100% reflection coefficient. This means that 100% of the GPR energy that hits a metal object or boundary reflects, and none of the energy transmits through the metal. This is why metal objects are the easiest objects to detect with GPR. Now, the #1 application for GPR in the world is utility locating. The reason that GPR is so popular for this application is because it can detect non-metallic utilities such as plastic and concrete pipes. Therefore, I suspect that many people in my audience today are utility locators. So I want to talk specifically about the reflection coefficient of utilities and how GPR detects them. GPR detects utilities because of the contrast they have with the surrounding soil. If the utility is made of metal, the reflection coefficient is 100%, as we've just discussed. What you may not realize is how GPR detects non-metallic utilities. The energy that reflects from a plastic pipe is not actually reflecting from the plastic. It reflects from the material inside the plastic pipe. That is what provides the contrast that causes GPR energy to reflect. So, it is the water, other liquid, or gas inside the pipe and the water content of the soil outside the pipe that dictates the reflection coefficient of that non-metallic utility. In the chart here, so for example, going from a dry sand with a K of 5 to water in a non-metallic pipe with a K of 80 gives a reflection coefficient of 60%. Good chance of success. The exact same situation, a water-filled non-metallic pipe with a K of 80, but now in a wet soil with a K of 25, has a reflection coefficient of only 28%, significantly less. Now let's look at gas-filled non-metallic pipes. When going from a dry sand with a K of 5 to a gas in a non-metallic pipe with a K of 1, the reflection coefficient is 38%. Again, let's saturate the soil with water, so now it has a K of 25, and look at how the reflection coefficient changes. The reflection coefficient is now 67%. Besides metal, one of the highest reflection coefficients yet. So, if you want to have a better chance of finding a non-metallic gas line, wait until the wet season, when the ground is saturated with water, and you might have a better chance. This just might be information that you're not expecting to hear. Okay, let's look at an actual utility data example. Here you see theory in reality. One hyperbola has a significantly stronger response than the other. Since they are at the same depth in the same soil, we assume the attenuation is similar for both. So the only explanation for the difference in signal strength is the composition of the utility or the material inside the utility. So in this case, one interpretation may be that the pipe on the left is a metal pipe and the pipe on the right is a non-metallic pipe. What I would like you to understand from this whole discussion is that when you look at a GPR line, you should be thinking that it is an image showing the contrasts between layers and objects. Some are large contrasts that produce strong reflections, while others are more subtle contrasts that produce weaker reflections. This is a geological example, and again, I know a lot of you are utility locators, so here's a utility example. Look at this image from a contrast perspective. Here are strong hyperbolas. Here's a weak hyperbola. Here's a strong hyperbola that is deeper than a weaker, shallower hyperbola. There's information in these observations that will help you interpret your GPR data better. When we zoom in to this area, we can see weak hyperbolas. I want to emphasize that those are real objects in the subsurface. I've heard people say phantom hyperbolas. I don't know what those are, but I don't believe that phantom hyperbolas exist. A hyperbola, whether it is strong or weak, is a reflection from an object. The strength of the hyperbola is due to the contrast between that object and the surrounding soil, as we've been discussing. In this case, because I see strong hyperbolas deep down, I might ignore these weaker hyperbolas and interpret them as being from an object that has a similar K value as the soil, like something like rocks, clumps of dirt, things along those lines. But if I was looking for utility that might be subtle, a fiber optic line, a non-metallic water line in a wet soil, or a non-metallic gas line in a dry soil, I should take a second look at these hyperbolas and collect more information to see if I see them again on parallel lines. If so, this would mean that they form linear objects, and this usually indicates a utility. Okay, let's move on to other things. A short discussion about the shape of GPR signals. As you saw in the earlier animations, GPR signal is a wave. It has troughs and peaks, typically 2 troughs and 1 peak, but it could also be 2 peaks and 1 trough. It doesn't really matter. The point is that reflections mimic the GPR signal. Reflections consist of these 3 bands of signal together. The white band has no meaning independently of the black band. Together, all 3 bands represent the reflection. New topic. I know that you all know this because it's intuitive. GPR signals get weaker as they travel deeper into the subsurface. But let's just make sure that we understand what is really happening. Reflections are always weaker than the amplitude of the signal that was transmitted. There are actually several reasons for this, but the dominant reason, and the one that I want to talk about today, is attenuation. The depth that GPR signals travel into the subsurface before they are completely absorbed or attenuated is controlled by the electrical conductivity of the soil or rock. We know this more commonly as clay is bad for GPR. But the underlying cause is that clay-rich soils generally have a high electrical conductivity. Here's an animation that shows what happens to the GPR signal as it travels in materials with different electrical conductivities. On the left, low electrical conductivity results in slower absorption of the signal and a lot of reflected energy making it back to the surface. Because, remember, we can only detect the object or boundary in the subsurface with GPR if the energy reflects and makes it back to the GPR receiver on the surface before it gets completely absorbed. In the middle is a material with higher electrical conductivity. The GPR signal is attenuating, but a little bit of signal makes it back to the surface. We would see this object, but it would be weak. On the right is unfortunately what many soils are like. They have high electrical conductivity and absorb the GPR signal quickly. In this case, the GPR energy makes it down to the object and reflects, but then it is completely absorbed before it makes it back to the surface. This object is invisible to GPR. Most GPR practitioners have been in this situation, trying to explain to the client why the GPR did not find the object they are looking for. The culprit is soils with high electrical conductivity. The soil may naturally have high electrical conductivity, such as clay soils, but materials with high electrical conductivity can also be introduced to the soil. In this data example, a chloride-rich leachate with high electrical conductivity was found migrating from a landfill site. The native soil is very sandy with low electrical conductivity that allows GPR to penetrate 20 plus meters. However, in the area with the electrically conductive leachate, the penetration is reduced dramatically to just 1 or 2 meters. We have had a long discussion about the two properties that affect your GPR survey more than any others. Now let's move on to how these properties affect us finding objects and boundaries in the subsurface. Let's think about all the things that we might be interested in detecting in the subsurface. Long, linear, cylindrical objects, pipes, cables, rebar, tree roots. Large diameter cylindrical objects, large diameter pipes, storage tanks. Tall cylindrical objects, metal or plastic drums. Long, linear but rectangular objects, things like duct banks, foundation walls. And then you have everything else. Small objects, spheres, cubes, everything in between, various point objects. So those could be rocks, debris, all kinds of objects fit this bill. And then you have boundaries, going from one material to another material over a larger area. Now let's discuss how these objects appear in GPR lines. At the same time, I want to discuss other signals that appear in GPR lines that you need to be aware of. I've shown a few slides with hyperbolas, but have not really explained why we see them in GPR lines. Hyperbolas are formed when a GPR survey line crosses over a point target. What I mean by this is that either a true point object, such as a buried cannonball, or a linear object, such as a utility that the GPR has crossed perpendicularly. The reason you get the hyperbolic shape from such an object is because the GPR is not a laser beam that only sends signal directly vertically into the subsurface. Instead, GPRs send energy into the ground in the shape of a cone. This means that as you collect data with the GPR system by pushing it along a line, there's energy going ahead of you and behind you. And this energy can reflect off objects and boundaries in the subsurface. Here's the poor man's animation that shows this concept. Cone of GPR energy radiating under the GPR as you push it along. When that cone of energy intersects with the object, you start to see it as the tail of a hyperbola, even though the object is ahead of the GPR. As the GPR gets closer to the object, the tail response moves closer to the surface. When the GPR passes over the object, that is the closest approach the GPR gets to that object, and that forms the top of the hyperbola. Then, as the GPR moves away from the object on the far side, there's still GPR energy traveling behind the GPR and reflecting from the object. This forms the other side of the tail of the hyperbola. Finally, the GPR gets far enough away from the object that the cone of energy is no longer intersecting with it. That is how and why a hyperbola forms. Here's an image that shows reality, the pipe, and the way the GPR sees it, a hyperbola. The object is always located at the top of the hyperbola. Use the top of the highest band in the GPR data to measure the depth. The way that utility locators track a utility is to find a hyperbola that they suspect is a utility and then run lines parallel to it to see if they see the same hyperbola on other lines. If they do, they usually mark the location of each hyperbola on the surface and see if the hyperbolas form a path that one would expect a utility to follow. One of the things that increases your confidence that you are following the same utility is when the hyperbolas look similar. That is, they are at the same depth and have a similar shape or character. In this example, all the hyperbolas are very similar. As a locator, that should make us feel good. Here's another example of the same thing, but this time with multiple utilities. Using the depth and shape as a guide, it's not hard to match up the hyperbolas and suggest that there are 4 different utilities crossed in this GPR lines. So there's utility number 1, very similar look and depth. Number 2, again, similar look and depth. Number 3, right in here in line, and number 4. We would probably bet money that if they had to push the GPR system slightly further on line 3, they would see the 4th utility on it. Okay, we know that crossing a linear object at 90 degrees gives you a hyperbolic response. Let's discuss what happens to the GPR response when the linear object is crossed at a different angle than 90 degrees. For example, what happens if the GPR crosses the linear object at 45 degrees? The hyperbola still looks like a hyperbola, but it gets wider. Tougher question. What happens if the GPR crosses along the length of the linear object? This tends to throw most people a bit, but the correct answer is that it becomes a straight line. This is because if you think about it, you get a hyperbola because the distance from the GPR to the object is constantly changing. You approach it, go over it, and leave it behind. But when the GPR runs right along the top of a linear object, the distance between the GPR on the surface and the linear object in the subsurface is constant. So you get a response at a constant depth in the GPR line. And that's what we see here. Let's look at an example of this. A utility locator collected 4 GPR lines. 3 of the lines are perpendicular to the utility and they show hyperbolas. The operator put marks on the ground corresponding to the position of the hyperbola in each line to define the path of the utility. Then they collected the 4th line running along the top of the utility. Here's the data. Lines 1, 2, and 3 are along the bottom. I want you to notice a few differences about the 3 hyperbolas. Number 1, the hyperbolas are different depths. That means that the object is getting deeper each time we cross it. This means that it's sloping. Number 2, the hyperbolas are slightly different shapes. Notice that the shallower hyperbola is pointier, and the deeper ones are more and more rounded. This is a geometric effect. Shallow hyperbolas are pointier and more like an inverted V. As the object gets deeper, the top of the hyperbola gets rounder, more like an inverted U. Number 3, the shallowest hyperbola is the strongest, and the deepest hyperbola is the weakest. This is not surprising. It's because of attenuation. The energy that reflected from the utility at its deepest point traveled that depth twice, and it's being attenuated the whole way. So it's not surprising that that signal is weaker. Now let's look at line 4 that goes along the top of the utility up here at the top of the page here. That dipping reflector, this dipping reflector right here is the utility. It's the top of the pipe. And clearly we can see that the pipe is sloping, which is what we predicted from seeing the hyperbolas. Now pretend for a second that you have not seen lines 1, 2, and 3, and that you are just interpreting line 4 on its own. I know that based on what I see in the line, I would interpret the sloping reflector as a boundary. Perhaps the bottom of fill, the top of the native soil, or a bedrock surface. Of course, we know that this interpretation is completely wrong. But this is what often happens when you interpret data with limited information. The lesson here is always collect data in several directions. Seeing the hyperbolas on the lines in the other direction instantly changes our interpretation to the correct one. Here's the full interpretation of what we're seeing on these particular section here. Now, you do not always cross linear objects at right angles, so be aware of the distortions that you'll see when you cross an object at an angle. Here are some examples from a course I did in Florida. Broader hyperbolas indicate that you crossed a utility obliquely. Here's a few good examples here. Misshapen hyperbolas may indicate that you or the utility are changing direction. To determine the path of the utility, there is more work to do if you get results like this. Okay, if we look back at the GPR line we were interpreting earlier, we also notice reflections from boundaries. From all our earlier discussions, you now know that these reflections are caused by layers with different dielectric constant values above and below. For example, we know that this boundary here is being caused by different material above and a different material below energy is reflecting. I've often looked at this line and said, I wish they had collected a bit longer because I'd really like to know what is going on here to the right-hand side. Okay, continuing to interpret this line, we notice a strong white, black, white signal at the top of the section. What is this signal? You're going to see it on the top of every GPR section, but where is it from? Let's have a look at what happens when a GPR sends signal into the ground. Most GPRs have a transmitting antenna. and a receiving antenna. When the transmitter fires, the very first energy that arrives at the receiver is the signal that travels through the air at the speed of light. This is called the direct airwave. There is also energy that travels along the ground surface at ground velocity that arrives at the receiver a few nanoseconds after the direct airwave. This is called the direct ground wave. In seismic, this would be called ground roll. Now, of course, the signals we are most interested in are those that travel into the subsurface and reflect from objects. But the direct airwave and ground waves are together. When we put them together, they're called the direct arrivals. They are so close together that they constructively and destructively interfere with one another and appear typically as three bands at the top of the GPR line. You don't see them as two separate events unless the antennas are quite far apart, something you only see in a CMP type survey. The direct arrivals produce these high amplitude bands at the top of every GPR line, and they can mask the weaker reflections from shallow reflectors. To see the reflectors under the direct arrivals, it's very common to use a background subtraction filter to remove horizontal events like the direct arrivals. Here you see background subtraction being applied to this section, and you see how the flat-lying reflectors have been eliminated. The background subtraction filter is in all our GPR systems, and it's also in our data processing software called Echo Project. So notice how these hyperbolas, which are a bit harder to see when they're masked by the direct arrivals, are easier to see once we apply the background subtraction filter. But the caution here is don't use the background subtraction filter if you are interested in seeing horizontal boundaries. Notice this horizontal boundary down here, about 60 centimeters or so. We apply the background subtraction filter and it's pretty much been eliminated. So if you are looking for flat boundaries, don't use the background subtraction filter. Okay, back at this section. So if the bands across the top of any GPR line are the direct arrivals, what happened here? Why does the direct arrival change at this point on the section? You can see that it is different on the whole right side of this GPR line. The answer is that the surface conditions must have changed, and that changed the direct ground wave. In this photo, you see several different surface materials: grass, soil, concrete, asphalt. As GPR lines are collected across the different materials, expect the direct arrivals to change. So there is no possible interpretation error caused by the change in surface materials. I advise people to add a flag in the data as they go from one material to another. Or better yet, collect data with GPS so you can zoom in on these spots and see what was changing on the surface. Okay, back at the GPR line we're interpreting. Look at the bottom of the line. What is the signal that looks like a snowstorm or an old school TV station not coming in properly? Some of you will know that this is background noise. It's important to remember that a GPR receiver does not only record GPR signals. It records radio signals. So it will also record any radio frequencies in its bandwidth. This is called RF, or radio frequency noise. And if the depth setting for your GPR line is deep enough, you should always see the background noise at the bottom of the line. RF noise comes from many different sources: radio stations, TV stations, walkie-talkies, cell phones, military communications. The sun emits radio waves. The universe emits radio waves. The surface of the earth is immersed in radio waves at all times. So you will always see RF noise in your GPR data, even if the antenna is shielded. Keep in mind that the RF noise is usually about 1,000 times weaker than the GPR signals we are emitting. So you don't see the noise unless there are no GPR signals present. For example, here's a GPR line. It's 75 meters long and it's down to about 75 meters in depth. It's actually a pretty good area for GPR. You see we're getting about 25 meters of penetration. At the top of the section is the RF noise the GPR receiver recorded before the GPR transmitter fired. So that's up here, and so that's the noise before the transmitter fires. Then the GPR transmitter fires, and you don't see the noise anymore because the strong direct arrivals hit the receiver. Then the receiver starts to record the GPR reflections coming back from the subsurface. These signals get weaker and weaker as they are attenuated by the subsurface materials. Finally, the GPR signals are so weak they have the same amplitude as the RF noise, and we cannot differentiate them from the noise anymore. That is the depth of penetration. Then the GPR receiver records the RF noise until the end of the GPR recording window. But if your GPR depth setting is too short, you may not even see the background RF noise. There are times when you may have a local radio transmitter near your GPR survey location. When this happens, you may see their broadcast signals in your GPR data more strongly. Here's an example of this type of noise. We know that this is not caused by the GPR system because the signal actually starts before the GPR transmitter even fires at the top of the GPR line. In this case, the signal is pretty strong, but it's not completely overwhelming the GPR reflections. The data is still fairly interpretable. Still, you may want to find a time when they are not broadcasting and do your GPR survey then. Here's another example of external RF noise appearing in a GPR line from a nearby transmitter. Notice how periodic it is. If I show you the source of the noise, you will understand why it's periodic. As this radio transmitter rotates, it periodically sends signals in the direction of the GPR system. To me, one of the fundamental things you want to know about any GPR survey is, what is the depth of penetration? As I mentioned, the depth of penetration is the depth at which the GPR signals attenuate to the same amplitude as the background RF noise. So in this section, even though there's still GPR signal, it's buried in the noise. So the depth of penetration is effectively here. Sometimes the best way to see this is by increasing the gain value. So the noise is amplified to make it easier to see. So where the noise starts to dominate the GPR line at the bottom, look at the depth scale on the side. That's your depth of penetration. So in this particular example, somewhere around 6-7 feet or so. This completes part 1 of the basics of GPR data interpretation. But before you go, I have a quiz. Let's see what you've learned. So the way this is going to work is that I'm going to show you a GPR line and ask an interpretation question about it. The possible answers will be on the screen. Choose the one that you think is correct, and after 15 or 20 seconds, the answer page will appear. Enter your answer on that page. I will see the results and we will discuss the answers. Okay, question number 1. Of these 5 targets, which target is likely non-metallic? Now let me share the results with you. 79% of you picked number 2, 13% of you picked number 4, and 2% of you, or about 8% of you, picked other ones. So let's talk about this one. Correct answer is number 2. And number 2 is likely non-metallic. And the reason is all the other targets are at the same depth. And therefore, the signal attenuation is assumed to be the same for each one. Target number 2 is clearly a weaker response, which can really only be explained by composition. Now, those of you who answered number 4, I know why. It's because it's a very different looking response. All these other ones are hyperbolas. This one has a different response, but the strength of the signal is actually very strong. It's comparable to these other ones. And so that does not indicate that it's non-metallic. Okay, so hopefully you guys followed that one. We're going to actually discuss, the next webinar we'll discuss why we get number 4 actually in this one. Okay, here's question number 2. So the question is, what is the composition of the 2 targets? There's 4 possible answers there. And in a second, I'll give you the answer page. And I'm going to share the results with you. And this is interesting. This is actually what I expected. And it means, so the correct answer is actually 3. So 28% of you got that answer, that we cannot determine the composition of these 2 targets. And I know why 52% of you picked this answer, that number 1 is metallic and number 2 is non-metallic. But let's talk about that. You can't determine the composition because the objects are at 2 different depths. Most people answer that target 1 is metal and target 2 is non-metal because it is weaker. But because they are at different depths, we can't say this for sure. Target 2 may have the same composition as target 1, but it's weaker looking because the GPR energy had to travel through more material and got more attenuated by the soil during that journey. So the correct answer is number 3. We cannot determine any guess on the composition of these objects. Okay, so hopefully you follow that one. Okay. Question number 3. It's just one answer. There's only 2 possible answers here. And it is, here is data collected on a concrete floor. Was this concrete data collected in the basement or on the 2nd floor? So have a look at that image. Think about what you know about concrete. Okay, let me share the answer with you on this one. So 72% of you got it right, and that is that this data was collected on the 2nd floor. So the reasoning on this is that the very strong reflector under the rebar is the reflection from the concrete-air interface. The contrast from concrete to air is large and produces a high reflection coefficient. In the basement, there would be a concrete gravel interface, which would be much weaker because the dielectric constant values are so similar, they would produce a very small reflection coefficient. So the main thing to notice on this one was this very strong horizontal reflector, which we've interpreted as being the concrete air interface that is very strong. So it fits with the data. Our interpretation fits with the data. Okay, I'm going to hide. And let's move on to the next slide. Okay, 4 parallel lines a few feet apart. What is the most plausible explanation of what happened to the pipe on line 3? So we have a series of hyperbolas here. 1, 2, 1, 2. What happened on line 3? So the possible answers are localized high attenuation, the pipe is broken and full of soil, the pipe gets deeper, or the pipe changes direction. I want you to have a look, another few seconds, and then I'm going to switch to the answer page. Okay, now let me share the results. So 58% of you said localized high attenuation, which is the correct answer. So I'm happy to see that. 24% of you picked the pipe is broken and full of soil. It's a plausible explanation. It does actually fit the data, but I would suggest that it's not the most plausible answer. You can actually see that the attenuation is not just on line 3. On line 2, there's also this pipe is starting to fade out. And so number 2 is a possible answer, but I don't think it's the most plausible answer. And then as for the pipe getting deeper or changing direction, probably not too logical that the pipe would suddenly dive deeper in one spot. Maybe you guys have seen situations where that occurs, but I don't think that that's likely in many cases. Okay, next question. How do you interpret the vertical signals in the middle of this GPR line? So have a look at the 4 possible answers, and then I'm going to share that with you. So 88% of you got the right answer, an external radio frequency transmitter. Okay. Of the others, I don't think possible foundation walls. The thing that I like the system malfunction. The thing to note here is that the signals are present before the GPR transmitter even fired. So these are not GPR signals. This energy did not reflect from objects in the subsurface. So anything that suggests an object like a cave or foundation walls is not the right answer. But the vast majority of you got the right answer, so I'm happy to see that. Let's move on. Okay. Why is hyperbola 1 wider than hyperbola 2? All right, let's share that. And here's what we've got. So the correct answer is that it was crossed at an angle. And that's why. Remember that when we cross a linear object at an angle, the hyperbola tends to get broader. And let's see, who got 78% of you got that correct. Those of you that are talking about it shallower, you remember that you might be thinking about what I was talking about earlier, that shallower hyperbolas are pointier. This is actually the inverse. This is the opposite of what I talked about earlier. Shallow objects should be pointier, not more round. So hopefully if, this explanation or this image here makes you understand why this hyperbola is broader than the other one. And I know you can't see that. I got to hide that. Okay. So again, we've got crossing the hyperbola or crossing the utility at an angle that caused that. Now, it is possible that it is an object with a much larger diameter, but I'll note that that was not one of the answers. And we're going to talk about that in the next interpretation webinar. Okay, next one. Question 7. Where's the gravel layer? Is it area 1, area 2, area 3, or area 4? That, and let's share. All right, total split. 25%, 31%, 31%, 37%, 8%. Well, the answer is you can't tell. It's a trick question. GPR does not detect the composition of a material. If it did, I would buy the GPR system that detected gold and make my fortune. GPR images show the structure of the subsurface. Now, there may be some geologists out there who could look at this image and based on the structure, determine the area that's most likely for a gravel deposit. But that would be an interpretation based on the structure. The GPR does not give us composition. So sorry to trick you on that one, but it's an important concept that you cannot expect composition. Okay, question 8. I warn you, there's actually 10 questions, so we're getting close to the end here. Question number 8. What's happening in the concrete? So again, this is a concrete example. You can see the rebar, or actually wire mesh reflections. There's some utilities underneath here. But there's something going on in this area. And the question is, what do you think is happening in that area? 67% of you got it right. I applaud you on that one. It is a void underneath the concrete. So those of you that didn't get that answer, let's discuss it. All we know from, let me show you the image here. Let's go back to the image. All we know from the GPR line is that there's a strong reflector inside or under this concrete floor. So that eliminates high attenuation or deterioration. I would suggest that cracking would be a more localized phenomenon and not a few meters across. So I think the most logical answers is a void under the concrete. If it's an air-filled or water-filled void, there will be a large contrast with the concrete and produce a strong reflector, which is exactly what we see in this image. Okay, question 9. Why are there no reflections here? Look at this section. There's a lot of reflectors, a lot of very chaotic reflectors, but in this one zone in here, there's no reflectors. And the question is, why? Okay, so let me share the answer with you. 54% of you picked that it's homogeneous, and that is the correct answer. For those of you who did not pick homogeneous, let's talk about this. Now, this answer is a fundamental part of GPR. The answer to this question is a fundamental part of GPR. The answer is that there are no reflections here because the soil in this area is homogeneous or uniform or constant. There's a few terms that you can use for it. Because of this, there are no contrasts, and therefore there is no reason for GPR energy to reflect. There has to be a change in properties or a contrast in materials for GPR energy to reflect. Remember that. That's absolutely fundamental. Most people, not most people, but some people will say that the area is a void or it's water or something else very specific. That answer is not technically wrong because those materials are homogeneous, but we can't tell the composition from GPR data. So we can't exactly say what the material is. The best answer is that whatever the material is, it is homogeneous or uniform. Now, some of you said that there is no GPR signal in this area because of high soil attenuation. That answer is not correct. And the reason for that is because if it was high attenuation, we would not see any signals down below. But we do. We see reflections down below this area. All right. Okay, last question of the day. So here's the last question. What is causing the strong reflectors at about 1.6 meters? So have a look at that. We've got a section here with a very strong reflector at the bottom. Let's have a look at the results. So 62% of you said bedrock, 22% cavity, 11% RF noise. The answer is none of the above, which I should have had. I'm sorry, I screwed this one up. I didn't make that one of the results. The GPR line is so out of context that you could never be expected to interpret it correctly. It would be pure guess. However, once the data is put in context, so let's have a look. the answer here. Let's unhide this so you can see something that's going to help you understand this image a lot better. Once the data is put in context by seeing the photo of where it was collected, the interpretation that is where the reflection is from turns out to be the more obvious. It's the far side of the stone block. The lesson here is that you must use all the information available to you to make the best interpretation of your GPR data. That includes map location, photos, as-built drawings, Google Earth images, field sketches, all things that put your data in context. You are going to interpret data differently from a street in the city than on the side of a mountain. Context is very important. So that completes today's webinar. I hope you've learned something useful to make you a better GPR practitioner, and I thank you for attending. And remember, all the previous webinars are also recorded and they're available on our website. Part 2 of this webinar, I'm going to call it GPR Data Interpretation Basics Part 2, is scheduled for Wednesday, September 12th. And so watch for your email invitation. So please feel free to contact me with any questions that you have using the email address listed on the screen. Until then, bye for now.